Hello students, today I will further continue my discussion on Gauss theorem. In my previous video, I have already discussed area vector, solid angle, electric flux and introduction of Gauss theorem. Today I will furthermore elaborate what is Gauss theorem, how we prove it, how we apply it, Gauss's theorem. And the statement of Gauss theorem, as you know, is that the total electric flux, through a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. Here epsilon naught is permittivity of free space, and you know its value is 8.85 into 10 to the power minus 12. Here epsilon naught is permittivity of free space. We consider relative enclosed surface. A closed surface encloses a charge Q. Then, according to Gauss theorem, the total flux through the surfaces of closed surface phi equals to Q by epsilon naught. Let a closed surface encloses a charge Q. Then, according to Gauss theorem, Gauss's theorem, the total electric flux through the closed surface is given by phi equals to Q by epsilon naught. As you know, phi equals to, here phi represents flux through total flux through the closed surface, as phi is dot product of electric field vector and area vector. Hence, E dot d is surface integral of E dot d is equals to Q by epsilon naught. This is the relation from the Gauss theorem. Now I will prove Gauss theorem with the help of Coulomb's law. Actually, Coulomb's law can be derived with the help of Gauss law, and Gauss law can be derived or proved with the help of Coulomb's law. Both have similar statements but in a different form. Both apply different values but they state same things. Proof of Gauss's law. To prove Gauss law, we have to consider a closed surface. Let a closed surface encloses a charge plus Q. So, this is the closed surface under consideration, and this closed surface encloses a charge plus Q at point O. Now, at any point P, you can take this point anywhere, and we will consider an area element at that point. I am considering an area element at P at this point. I am considering an area element at point P. Let us consider an area element at point P at a distance r from O. We know that electric field at point P due to charge at O will be 1 by 4 pi epsilon naught q by r square. Electric field at point P due to charge q at O T1 equals to 1 by 4 pi epsilon naught q by r square. Now I will write out the board, but I have to save the diagram. Let the area element which we have considered at point P, the perpendicular to area element Pn, which is the direction of area vector ds, makes an angle theta with E. Let normal to the area element ds, normal to the area element ds makes an angle theta with E, electric field vector E. Then component of this E in the direction of Pn will be E cos theta. Then component of E in the direction of Pn equals to E cos theta. Now electric flux through this area element ds electric flux through area element ds d phi equals to E cos theta into ds. Now I will return to value of E 1 by 4 pi epsilon naught q by r square cos theta into ds. Now I will arrange all this. Q by 4 pi epsilon naught ds cos theta by r square. In the topic of solid angle, you have already learned that ds cos theta by r square represents the solid angle subtended by this area element at point 2. This is the solid angle subtended by area element at point 2, d omega. d omega is the solid angle subtended by area element ds at point 2. Therefore, flux d phi equals to q by 4 pi epsilon naught into d omega, where d omega is solid angle subtended by area element ds at point 2. To calculate total flux through the closed surface, to calculate total flux through this closed surface, I have to integrate this relation, this d phi over the surface of this enclosed surface. Therefore, total electric flux through the closed surface phi equals to integration of d phi. Here I have taken surface integral. Integration is of three types: line integral, surface integral, and volume integral. If the surface is taken over a surface, then it is called surface integral. Q by 4 pi epsilon naught into d omega. Q and 4 pi epsilon, all these are constants. Hence I take this out of the integration sign. In the topic of solid angle, I have discussed that a sphere subtends a solid angle of 4 pi at its center. Similarly, this closed surface will subtend an angle of 4 pi at point O. Hence, the surface integration of d omega will be equal to 4 pi. 4 pi. This and that cancel. Q by epsilon naught. Hence, therefore, flux phi equals to Q by epsilon naught. This is Gauss's law. Hence, the Gauss law, I have proved Gauss law with the help of Coulomb's law. Now, I will derive Coulomb's law with the help of Gauss law. Derivation of Coulomb's law. Derivation of Coulomb's law with the help of Gauss law. Let us here we consider a sphere of radius r with a charge plus q at its center. This is a sphere of radius r which encloses a charge plus q at its center. Let a sphere of radius r encloses a charge plus q at its center. The direction of electric field at point P due to this charge will be radially outward. From symmetry, it is clear that the magnitude of electric field at each point on the surface of the sphere will be same. From symmetry, it is obvious that magnitude of electric field at each point on surface of the sphere will be same. From Gauss law, now I will apply Gauss law. Applying Gauss law, equals to Q by epsilon naught as phi equals to integration of E dot ds. Therefore, integration of E dot ds equals to Q by epsilon naught. Now I consider an area element ds at point P. The direction of the area vector will be also in the direction of straight line OP. Here, in case of a sphere, the area vector and electric field are in the same direction as area vector ds and electric field E are in same direction. Therefore, theta equals to 0 and cos theta equals to 1. Therefore, integration of E ds cos 0 equals to E ds equals to Q by, because cos 0 equals to 1. E is constant for every point on the surface of a sphere. Hence, I will withdraw E from the process of integration. Now, E equals to E into Q by epsilon naught. Now, the surface integration of area element ds will be equal to surface area of the sphere, and surface area of the sphere equals to 4 pi r square. Surface area of the sphere is equal to 4 pi r square. Therefore, E into 4 pi r square equals to Q by epsilon naught. Therefore, E equal to 1 by 4 pi epsilon naught Q by r square. Now we place the test charge at point P. Then force on that this test charge will be F equals to Q into E, where Q is the magnitude of charge and E is the electric field. Now we place a test charge Q naught at point P. Then force on test charge. F equals to Q naught into E. Now you place the value of E from the equation 2. 1 by 4 pi epsilon naught Q naught by r square, which is Coulomb's law. Thus, I have derived Coulomb's law with the help of Gauss law, and as I have stated in my previous discussion, that Coulomb's law can be derived with the help of Gauss law, and Gauss law can be derived with the help of Coulomb's law. Application of Coulomb's law. I will take an example. I will find electric field due to an infinitely long straight charged wire. Application of Gauss law. Application of Gauss law. My first example is electric field at a point due to an infinitely long straight charged wire. Straight charged wire. Listen. This is an infinitely long straight charged wire. Let charge per unit length of wire be lambda. Let charge per unit length of wire equals to lambda. Now I consider a section. Now I take a section of this infinitely long charged wire. We take a section of infinite. Sorry, I have missed written. Around there. We take a section of infinitely long charged wire. Now I consider a cylinder of height h and radius r coaxial with this wire. This cylinder is of height h and the radius of the cylinder is r. Let us consider a cylinder of height h and radius r coaxial, that is the axis of cylinder coincides with this charged wire. Let us consider a cylinder of height h and radius r coaxial with the wire. This cylinder